All right, guys, this is going to be our first lesson on the topic of force, which is a really big topic in physics. And we'll be with it for, well, more than 2 chapters, but the next 2 chapters, next 2 units will be on forces and Newton's laws. Newton has 3 famous laws, which are kind of the backbone for our understanding of how to deal with force and its relationship to motion in physics. But before we get to them, and I'm going to spell them out at least a little bit here in this video, but before we do, I want to talk about what are forces. So let's start there. What is a force? Force is merely, just to put it in kind of common everyday speech, it's just a push or a pull. And there are lots of different ways in which forces might be exerted, but there are either pushes or pulls. That, by the way, the idea that it could be a push or a pull implies that direction matters. That means it is a vector quantity, which is measured in the unit of the Newton, named obviously after Isaac Newton. The Newton as a unit, which we'll be abbreviating with a capital N, there's 2 ways you might think about it. The sort of maybe less intuitively obvious way that comes directly from Newton's second law is that this is the amount of force it would take to accelerate 1 kilogram 1 meter per second squared. I don't think that's super intuitive, but it's technically accurate. To give you maybe a little bit more of an intuitive sense, you could think of 1 Newton is roughly equivalent to the weight of 1/4 pound. So if you imagine holding a cheeseburger in your hand, the amount of force that you have to exert to hold up that cheeseburger is roughly speaking 1 Newton. So it's a little bit on forces, and we'll be talking about forces moving forward. So let's get started with Newton's first law. I'm actually going to deal with the laws slightly out of order. I'm going to deal with Newton's first law first, and then I'm going to go to the third law, and then the second law we'll do last. So the first law is, I think, a fairly well-known law. You might not have ever heard it referred to as Newton's first law, but I bet you've at some point read or even had to memorize a sentence that sounded something like this. An object at rest will remain at rest. An object in motion will remain in motion in a straight line at constant speed unless acted upon by an unbalanced force. That long statement, I'm not going to bother to write it out. You can rewind it if you want. You rewind the video and copy it down if you care to, but I'm going to write it in a slightly more succinct way. And Newton's first law is, I think, kind of non-intuitive, and I'll explain why. But the way I'm going to write it is this: objects accelerate if and only if there's a net force applied. So we should probably break this down a little bit. First of all, the first thing I want to emphasize at the outset here is that the relationship, according to Newton, is between force and acceleration. And that's sort of the root of what I think is counterintuitive. Most people, and I suspect all of you at some point, are going to want to say to yourself that the relationship is between force and velocity. So for instance, you might say, oh, I know that the net force on this object is 0 because it's not moving. And that would be an insufficient or potentially even wrong statement. The relationship, according to Newton's first law, is between force and acceleration. So anytime you are going to say anything definitive about the force on an object, you have to talk about the object's acceleration, not its velocity. Don't tell me it isn't moving. Tell me, I know the net force is 0 because the acceleration is 0. Or I know that the net force isn't 0 because the acceleration isn't 0. So I'm going to hit this again many times because I think it's non-intuitive. But again, the relationship between force and acceleration. It might be worth saying something about net force. Net force is just a term that refers to the total force when you've added the vector sum of all of the forces. So it's sort of you could think of this, if you like, as in terms of vector term, this is sort of the resultant. The resultant is the net force, what you get after you've combined all of the forces on an object. So again, I think non-intuitive, but really central to our understanding of force. And that's all I'm going to say about this, Newton's first law, right now. Newton's third law, let's go there. Newton's third law is sometimes called the action-reaction principle. I bet you've heard something, at some point in your life, you've heard something like, for every action, there's an equal and opposite reaction. I'm going to try to be a little more precise, and I'll say that whenever one object exerts a force on a second, the second exerts an equal force back on the first. And the two words I want to highlight in this sentence are that the second exerts an equal force, that means equal in magnitude, back, meaning opposite direction, on the first. We could write this if we wanted in equation form. I could write something like F12 has to equal negative F21. Anytime one object exerts a force on a second, the second exerts an equal force back on the first. Where this often comes up is this idea that let's say I'm walking along. You might think that if a person is walking along here, there's a temptation. Let's say here's the ground, and here's some person walking or running or whatever. There's a temptation to think that you move yourself, that you, in some sense, are pushing yourself. And certainly you're responsible for the fact that you're moving, but of course you don't push on yourself when you walk. What's the thing that pushes on you? Well, you push on the earth. If we were to zoom in really closely here, you see that what's actually happening is that you push on the earth, right? This is a force here. I'll make it even bigger. There's a force of you on the earth. You're pushing earth. And in fact, earth is being pushed upon. You don't notice the earth accelerating because it's so big. But when you push on the earth then, action-reaction, pushes back on you, like so. So these two forces, according to Newton's third law, have to be equal. Forces always come in pairs, and the forces, these pairs of forces are always equal and opposite. So you push on earth, earth pushes on you. There are times in which identifying action-reaction pairs can be a little bit tricky. So for instance, let's imagine a separate case here. What if we had a table? Here's the ground, and I've got like a table here, and on the table I've got a book. And what if I said that the action is gravity on the book? There's a force of gravity pulling the book down. If I were to zoom in here, right, we know that there's a force of gravity pulling down right here. You might be tempted to say, oh, well, the equal and opposite force to that, the reaction, must be the normal force from the table, and that would be wrong. It is true that the normal force from the table is equal and opposite to the force of gravity on the book, but they're not an action-reaction pair because they don't involve the same two objects, right? It's one object and a second object. There are two objects involved, and the force has to be between the two objects. So what are the two objects that are involved with gravity? Well, it's the book and the earth. This gravity is the earth pulling book down. So the reaction to that is the book exerting an upward force on the earth. And that isn't a real force. There is a sense in which the book exerts a gravitational pull upward on the earth. Again, you're never going to notice it, but that's the action-reaction pair there. Finally, so these are really sort of, these two laws, I think, are really more conceptual in nature. They help you understand what's actually happening on a conceptual level with forces. And usually, as a practical matter, usually in problems where these are coming up is if you're asked to explain how you know something, oftentimes you have to make a recourse to either mentioning the first law or the third law. The second law, which we'll come to now, is actually an equation. And this is the law that you're going to be writing out. You're going to find yourself writing out quite a bit in this course. In Newton's second law, I'll just write it right away as an equation. It's maybe the most famous equation in all of physics, is that F net, the net force on an object, is equal to its mass times its acceleration. I'll write that a little more clearly. F net equals ma. And this is just, and I mean, it's impossible to overemphasize how important this equation is in physics. It's really, central to our course. So F net equals ma. I'll just point out that the force here is the net force on the object. You'll be using this equation quite a bit when solving problems, and really Newton's three laws, and the second law in particular, are best understood by doing practice problems. And you are going to do a ton of practice problems on your problem sets. And hopefully through the course of doing those problems, you'll understand these laws better. One thing I want to give you right away, though, is a three-step process for solving problems. So a three-step problem solving method for using Newton's second law. So here we go. Step one, you have to determine the system. And I'll just remind you that in science, in physics, when we say the word system, what we mean by that is, I'll choose a different color here. What we mean by the system is the object that you are thinking about, the object that's in consideration. So in some cases, there might be a setup where there are several different objects involved, maybe multiple blocks connected by a rope, for instance. And you have to determine what is the object that you want to consider. If you're using F net equals ma, what's the object that you're going to consider the net force upon? What is the mass of the object that you are considering, and what is its acceleration? So you have to determine the system. What is the correct object to think about? And that can be at times tricky. Sometimes it's obvious what the object is. Sometimes there's only one object involved. Once you've determined what object you want to consider, then you move on to draw the free body diagram for that object. And I'm going to say a word about what a free body diagram is for those of you who may not remember. What is a free body diagram? All a free body diagram is a diagram where I take a situation and I draw all of the forces that are acting upon it. So for instance, maybe I'll start here. I'll give an example of an FBD. Let's imagine I've got a ramp and a block on the ramp, and we're told that the block doesn't move. The block is stationary or static upon the ramp. Well, I might ask myself, what are the forces acting on that block? And to draw an FBD, what I'll do is I'll represent the object that I'm considering as a dot. And by the way, first step of the problem here, or the first step of our three-step method, was to determine the system. In this case, the system is the block. Fairly obvious. There's really only one object. So whatever you've chosen as your system, that becomes a dot. So in this case, the dot is representing the block. And now I'm just going to draw the forces that are acting on that system, on the block. So I'm going to draw an arrow for gravity. Gravity pulls down on the block. And the way I label this, I'm not going to write gravity, I'm going to write mg. And in physics, mg is understood as the force of gravity. This is what's known as the weight of an object. Remember that mass and weight are different. The mass of an object is just a measurement of how much matter there is, how much stuff there is in an object. It does not depend on the amount of gravity in a particular location. Your mass is the same no matter where you are in the universe. However, your weight is the force of gravity acting upon your mass, and that, of course, will vary. If you go to the moon, your weight's different. Your mass is the same, but your weight is different. So we will use mg as weight, and of course, how you calculate the weight in newtons is to take your mass in kilograms and multiply by g, 9.8. All right. There's a force, of course, from the ramp itself, right? This ramp is solid, and it's going to push on the block perpendicular to the ramp. And the word for this kind of perpendicular force, a force perpendicular to a surface, is called the normal force. So I'll write N here for normal force. That's the way I abbreviate the normal force. Normal, again, just means perpendicular. This force is perpendicular to whatever the surface is. So you might stop there, but of course, if these were the only two forces, we wouldn't have a static situation. Static means that the acceleration is zero. But we know that the acceleration we know that the acceleration will only be zero if the net force is zero. So we need to have a way to write that the net force is zero. And the only way for the net force to be zero is to add an additional force. And I want to explain how I know that. I could go ahead and split the mg vector, this vector right here, into components. There is a portion or a component of mg acting into the ramp. That's this component. I could write it as mg perpendicular. Sometimes the way this gets written, and the way I think I will write it actually, is I'll consider this to be the y direction. For my purposes, I'm going to call this direction, I'm going to rotate our coordinate axes. So the y direction is now parallel to the ramp, and the y direction is perpendicular to the ramp, x is parallel. So this is the y component of mg, and here is the x component of mg. By the way, on the diagram, you can convince yourself of this. Whatever the angle of the ramp is above the horizontal, whatever that angle is, this angle right here is also that angle, as I've drawn the picture. Whatever the angle above the horizontal here, it's going to be that angle there. So that means that mgy here is going to be equal to mg sine theta, cosine theta, and mgx is going to be given by mg sine theta. So now, if we look at this, a is 0. That means ay has to be 0, which means these two y forces have to be equal, right? These two have to cancel in order for ay to be 0. But ax must also be 0, which means that I need another force to cancel this one. mgx, the mg sine theta, whatever that is, I need a force to cancel it. So I need another arrow acting opposite from this vector right here. I need another arrow opposite of that vector and equal in magnitude. And you might ask yourself, what is that force? What is preventing that block from sliding? And of course, it's a static friction force. We haven't talked about friction. In fact, friction, how we deal with friction mathematically won't come up until our next chapter. But so now I have a free body diagram. I've drawn the object, and I've drawn all the forces acting on the object. One small but important point, when you're drawing a free body diagram, you actually shouldn't have components. There should be no components when you do a free body diagram. So I'm actually going to go ahead now and erase these because they shouldn't be there. And so now I've drawn my FBD, the three forces that are present. And you'll have an opportunity to practice doing this. So back to our system, or to our method. We've determined the system, right? You draw the FBD, and then you move into F net equals MA. Once you've got your free body diagram, you are prepared now to look at those vectors and determine what the net force is. And at that point, it's usually a fairly straightforward calculation once you've done steps 1 and 2. Steps 1 and 2 are the hard part. Step 3 is easy. All right, that's enough information, I think, for right now. As I said, I just want to reiterate something I said earlier, which is the best way to learn this, the best way to gain mastery with this stuff is to do lots of practice problems, and you will be.